So something to think about when trying to decide, do I deprotonate versus an addition step? So the hardest one to kind of figure this out with is the strong base hydroxide, NaOH. A lot of times it's NaOH. And the problem is this can be a base, and it can also add into carbonyls. So depending on your type of carbonyl, that's what you need to look for. So if it's an aldehyde, or when it's a ketone and an aldehyde, the addition step, while that can happen, there is no good leaving group. So it's not as likely. Or it will happen, but usually what's more likely is you're going to deprotonate the alpha CH. If you see an ester or an anhydride or an ester, what's going to happen with this? These are going to turn into carboxylic acids. So addition is going to be more likely. Carboxylic acids. So there's a clear difference when you have something like this that's going to deprotonate ketones and aldehydes and turn, right? Acid chloride would be another one, and acid chloride would also turn into a carboxylic acid. Okay? Now some trickier ones, when we're trying to think about deprotonation versus addition. What if I did this ester and I reacted it with this base? So now remember we talked about matching the ester with the base. So even if this reacts and does addition, you're going to get back the same ester, right? So then it's going to be about the deprotonation. Then it's going to be about the deprotonation. Another thing you can do to make sure, if you want to make sure you do deprotonation, instead of having a small base, use some of those bulky bases. One of those bulky bases is lithium diisopropylamine, that LDA. Use a bulky base, right? That'll usually prevent addition because it's too sterically bulky, and it'll do more deprotonation of the alpha CH. So this is a question from Top Hat from 2513. It's from the homework questions from Top Hat. 2513, we actually did this a clicker question in class 2. The question asks, which of the following carboxylic acid derivatives that is the most electrophilic? Which one of these is the most electrophilic? So let's see if we can figure that out. I'll label A, B, C, D, and E. See if we can think of that, which one is the most electrophilic. So a couple things to think about, right? So we're really asking the carbon of the carbonyl in all these cases. Which one's going to be the most electrophilic and why? So either there's a more reactive starting material, and or it forms more stable products. So that's what we need to think about. So what we need to think about here is actually kind of the first thing we talked about when we talked about nucleophilic acyl substitutions is we need to think about what the leaving group is, right? Because what's going to happen here is we're going to do an addition. We're going to make a tetrahedral intermediate. And when you make a tetrahedral intermediate, what do you ask yourself? Do I have a leaving group? And then what is the best leaving group? So we need to look at essentially analyzing that. Well, I guess we'll have to analyze both of these, and then both of these too. So we need to think about what's going to be more stable. An O minus, an S minus, or an NH minus. And I even did these in a certain order. If you look at this looks like a periodic table, perhaps. Right? Where's nitrogen? Nitrogen's to the left of oxygen, and sulfur's below oxygen. Right? So you should automatically know, well, nitrogen's less electronegative than oxygen, which means oxygen's going to be able to stabilize a negative charge better, so it's going to be more stable. So that'd be a better leaving group. So you can automatically eliminate C would be a bad answer because that has, right, 2 leaving groups that aren't very good. And E has 1 that's not very good. What about oxygen to sulfur? What's the relationship there? Well, sulfur is lower on the periodic table. That means it's larger. Larger groups, right, up and down the periodic table, it's all about size. Across, left to right, right to left, is about electronegativity. size up and down in a column, a period, the larger you are, the more able you are to spread out that charge, which makes you more stable. So the best one is going to be B, because it has the best leaving groups, the most stable leaving groups. That's going to be the most electrophilic one. So taking a look at that sapling question, this is an interesting one. It asks you to think about a lot of things. Asks you to think about aldehydes versus ketones as far as reactivity goes. It asks you to think about carbon stability as far as ring size goes. Right? What are the size rings carbon likes to form? And then there's some enolate chemistry, and you do some cyclizations. And if there's some heat around, which I think there was in this, right, that should be a tip-off, right? When you see heat, you can think about not just an aldol type reaction, that's what this is going to be, but you can also think about condensations, which leads to conjugation. So first, let's number our carbons. 1, 2, 3, 4, 5, 6. Ask ourselves which carbons have alpha CHs that are acidic, right? How do I know that? Again, we're going back. Well, OH minus is a strong base, and aldehydes and ketones, right? They don't have good leaving groups, so even if the OH minus adds, there's really no OH minus is still the best leaving group, so they're going to be more prone to do enolate formation, acid-base chemistry, deprotonation. So which carbons have alpha CHs? 2 and 4, right? 5 doesn't, right? There's 2 methyls there. So 5 does not. So now the question is, okay, if I make an enolate here at carbon 2, so I put a negative charge there, what's it going to react with? So this is going to be the ketone side of this molecule is going to be my nucleophile, which means my aldehyde left over here is going to be my electrophile, because an intramolecular reaction is more likely to take place than an inter, right? Molecule can react within itself faster than it could with whole nother molecule someplace else. So that means this side is going to be my nucleophile, and this side will be my electrophile. So we need to ask ourselves, okay, if carbon 2 is a nucleophile or carbon 4 is a nucleophile, what would happen if they reacted with carbon 6? We know for sure carbon 6 is the electrophilic carbon. The question is carbon 4 going to be the nucleophile, or is carbon 2 going to be the nucleophile? So let's look at, so if carbon 2 is a nucleophile, it would form with carbon 6, so it would be a 1, 2, 3, 4, 5-membered ring you'd form. Because we're going to form a ring, right, because it's in the same molecule. If it's carbon 4 reacting with carbon 6, you'd have a 1, 2, 3 carbon ring. What do you think is more likely, 5 or 6 carbon, 5 or 3 carbon ring? 5, right? So 6 is the best, like chair conformations. 5 is next best, right? So that's what we're going to do. We're going to deprotonate here, make an enolate, deprot. All right, so carbon 2 is our nucleophile. Right? I just drew it in the enolate form. So carbon 2 still is our alpha carbon, still the nucleophilic carbon. It's not oxygen. Electrons come down. Pi bond attacks carbon 6. We're doing an addition reaction here, right? An addition reaction. Making a tetrahedral intermediate. So I can draw this pretty, or I want to draw it ugly first? Let's draw it ugly first. One, 2, 3, 4, 5, 6. So there's certainly the ugly version. Made a 5-membered ring. I can redraw it. I would just draw the 5-membered ring first. I know the bond I formed was between 2 and 6. 6 was bonded to 5, which is bonded to 4, which is bonded to 3. Carbon 1 is bonded to 2. Carbon 3 has a carbonyl, and carbon 5 has 2 methyls, and now carbon 6 has an O-. There you go. All right, then the next step, that water that we originally made from that first step, the O- is going to take that H. We're going to regenerate OH-. So a deprotonation. And that's going to make that traditional aldol product. I'm going to bring my carbons. That was a 1, 2, 6, 5, 4, 3. That's that aldol product, right? The alcohol. But notice at the beginning, right, we have heat. Remember, be careful about your temperatures. That matters. You can decarboxylate. You can do these condensations if there's heat around. So that's what this is going to do. And where's it going to, what kind of reaction is it going to do? It's going to do actually an E2 reaction. It's going to do a aldol condensation, right? Because that alpha hydrogen that's still there is pretty acidic. And we can actually just do an E2 reaction regenerating OH-. So that's an E2. And that gives us the aldol condensation product. It's ugly. Try again. OH-. Again, we made water. Number those carbons. 1, 2, 6, 5, 4, 3. There you go. Aldol condensation because of the heat. That's that last step, that E2 step. Point to bring attention. OH- is not a good leaving group, right? How are you doing this E2 reaction if OH- is not a good leaving group? Well, you're starting with OH-, right? So there's OH- in the system. And that also comes back to that energy. It's going to take a lot of energy to make this go, because OH- is actually not a very good leaving group. So that's part of the reason why you need that heat. But you also have OH- around too, so it helps. It's a good enough base, but yeah, OH- is a bad leaving group, absolutely. But you're making something that's conjugated, right? Water's a byproduct. You could dehydrate it, right? You have things you could do to force it towards this way, and then the heat really helps. All right, let's look at an acid chloride reacting with ethylamine. And the question here is going to be, why do we need at least 2 equivalences of amine or excess amine? Let's look at the mechanism and see why that is. It'll be clear to you pretty much one of the byproducts of this reaction, right? Because we know the product. We know what the product's going to be, hopefully. We know, right, it's going to be this, right? But what else is a product? Just by looking at the atoms, what else did you make? You made HCl. Oh boy. That's what the problem is. What's HCl? HCl is a acid. And the problem is this. Once this reacts the first time, imagine you have 3 things in your beaker. You have this and this, right? So one reaction, one of these molecules meets up. You have acid chloride, amine, and HCl. What's the most reactive species of those 3? So what's the best electrophile, best nucleophile? What's the most reactive species of those 3? HCl. And what is HCl? Is HCl electrophile or nucleophile? Is it electron rich or electron deficient? HCl? H plus, right? HCl becomes H plus. It's electron deficient, right? It's an acid. What do you know? Acids are all electron deficient. That's a problem. Why is that a problem? So now this is my best electrophile. What's an acid chloride? Is it an electrophile or a nucleophile? It's an electrophile, right? The carbon of the carbonyl is electrophile. But now this isn't my best electrophile. This is. What's my nucleophile, right? The amine is a nucleophile, of course. What's the amine going to react with? Which electrophile? The most reactive one. So that's the problem. That's why you need to have, when you do this kind of reaction, you need to have a lot of this around, because every time you make HCl, you need to react it with an amine if you want another amine to come here, right? So that's why you need 2, right? So you need 1 amine to react with all the acid chloride, and then you need at least 1 more that's going to react with the HCl, right? That's why you need excess amine.
But if you make H+, don't you make Cl-?
Yep. Then that's going to be then that's even better, because that's going to be a salt. So what you're going to make then is something like this, right? A lot of times sometimes they'll add pyridine in, and what you've made now, this thing, is a salt. Are salts going to necessarily be soluble in organic solvents? Nope. So now it's going out of solution. So it's like a solid crashing out of solution, which is just like a gas bubbling out, and that's going to help shift equilibrium. Exactly. All right, so this is problem number 4, chapter 26. You have two things. You have an aldehyde and a ketone. Step 1, aldehyde and a ketone, and a strong base, ethoxide. Aldehyde and ketone, so we're not worried about addition here. So we know it's going to be an alpha CH, a deprotonation. Strong base, we're going to make an enolate. Which is going to be my nucleophile, it's going to be my electrophile. So we have to look for the alpha CHs. Does the aldehyde have any alpha CHs? But what about this? That is not an alpha CH, for the love of God. That's an aldehyde CH. That's not an alpha CH. So we force ourselves. This aldehyde does not have any alpha CHs. No sp3 hybridized alpha CHs even. I would take it that far. So that means this is going to have to be my electrophile. It can't be my nucleophile. So it means the ketone is going to be my nucleophile. And how many types of alpha CHs does this ketone have? Just one, right? So it's symmetrical. So it doesn't matter what I picked. So I've numbered it 1. I've done some numbering here. So I picked 1, 2. So we're going to deprotonate at carbon 2. Make an enolate. So that's a good nucleophile. Where's that going to react? What's that going to react with? Which carbon number? 3, right? It's going to react with 3. Do an addition reaction. What's the last step going to be here? No, we made a tetrahedral intermediate. Are there any good leaving groups? Nope. So we're going to do a protonation then. Very good. So protonation. So this is the aldol product. The question is, are we done? So let me number my carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Are we done? Is there any heat involved? No. So we're on to step with H+, though. This is interesting, though. Or HCl. There is no heat with HCl. Huh. But wait. Why is this? It's going to react more. Why? So it is going to keep reacting. I just moved it over here. Now remember, think about, so it's going to do an aldol condensation. So we're going to end up with a pi bond here. Because why would you do condensation here without heat? Why would you not need a bunch of energy to do a condensation here? Because what kind of product are you going to make? Condensation will happen if it leads to, it's going to be a more stable product. Condensation leads to conjugation. If it leads to conjugation, also notice this is an aromatic ring. That's a benzylic carbon. Oh, that's aromatic. That's a really stabilized, right? What's going to happen here so we do a protonation. We're going to do a protonation. Now this is a little different. This is acidic conditions. But look at this. That's a really good leaving group. And it's a benzylic position. You're making a benzylic carbocation. So you're going to do what kind of reaction here then? So this is right, that's the leaving group. You're going to actually do an E1 reaction here. All right, this is the start of an E1. The water can come back in. Take the H that's here. All right, so it's deprot. And a lim. All right, E1 elimination. And the final product is the fully conjugated product shown. Right, so that conjugation leads to condensation without even the heat, without even a lot of heat. You can do that. So again, why will this happen? Is because, right, you can make a really stable carbocation because it's next to an aromatic system, and the final product, you'll notice, right, all these pi bonds, right, they're all in conjugation. So you're making a really stable product. It doesn't take as much energy necessarily to get there. That's why you didn't need the heat. So if this wasn't as conjugated, you absolutely need heat. You need to have some forcing. You need some more energy. So, right. So for instance, if this whole piece wasn't here, you would have to have heat to make this do a condensation. Right. The conjugation's making it easier because it's all conjugated. Because this is aromatic, it makes this a lot easier. If this wasn't here, oh man, you're gonna need to heat it up for sure, a lot probably.